A bolt is the smallest part in most machines and the one everything depends on, and in an acid bath, a furnace, or a strong magnetic field, an ordinary steel bolt corrodes, softens, or pulls where it should hold. A silicon carbide bolt answers with a fastener that does not rust, does not conduct, and does not lose its grip when the temperature or the chemistry turns hostile, threaded from a ceramic instead of a metal. Silicon carbide is chemically inert, so the bolt holds its threads in acids and alkalis that would eat a steel fastener down to nothing, with the single exception of hydrofluoric acid. That corrosion resistance is why these fasteners appear where the fluid, not the load, is the real threat. The material carries no free electrons to conduct and no iron to respond to a magnet, so the bolt neither shorts a circuit nor disturbs a magnetic field. And at roughly 3.15 grams per cubic centimeter, it weighs about 40% of a steel bolt the same size. Its Vickers hardness climbs above 23 gigapascals, so the threads resist galling and wear far longer than hardened steel, and the bolt keeps its strength above 1,200 degrees where a metal fastener would soften and creep. Hard, light, inert, and heat stable, the qualities a metal bolt cannot hold all at once. A ceramic bolt is strong in a particular way. Its compressive and tensile strength are high, but like all ceramics, it is brittle. It will not yield and stretch the way steel does before it breaks. So the limit that matters when tightening is the torsional fracture torque, the twist at which the thread would snap rather than give. That is why the working rule is to tighten a ceramic fastener to about half of its fracture torque. A 50% margin that holds the joint firmly while keeping a wide buffer against the sudden, brittle failure that over-tightening would cause. A torque wrench, not a hand feel, is what keeps the bolt inside that band. One more rule follows from the physics. Because silicon carbide expands far less than metal when heated, pairing a ceramic nut with a metal bolt, or the reverse, means the two grow apart at temperature, and the ceramic can split if the metal swells against it. Matching the thread partners to the service temperature is part of using the fastener correctly. Thread sizes follow the same standards as metal hardware. Metric runs commonly from M2 up through M8, imperial from the tiny 0-80 to around 3/8 16. And the head comes in the familiar styles: hex, socket cap, flat, and pan. So a ceramic fastener drops into a standard threaded hole. Where a standard part will not fit, the geometry is made to the drawing. Diameter, length, pitch, head style, and thread class are cut to match the joint, and threads are held close to standard class fits so the ceramic bolt mates with an existing nut. A non-standard length or an unusual head simply follows the print rather than forcing a redesign. Holding a flange or a pump housing together inside a chemical line, the bolt sits in the same acid or caustic that flows through the pipe, and it neither corrodes nor contaminates the fluid the way a rusting steel fastener would. Because it does not conduct, it also breaks the electrical path that drives galvanic corrosion between dissimilar metals, removing the very mechanism that eats a metal bolt in a wet, ionic environment. Tightened to about half its fracture torque with a torque wrench, it clamps the joint and keeps clamping as the chemistry works around it. Opened for inspection after long service, the threads come out clean and sharp where a steel bolt would have seized with rust and had to be cut away. The same fastener goes back in and torques to the same figure it did on the first assembly. Immovably, one small ceramic bolt does the one job the whole joint depends on, in the acids, the heat, and the fields that would defeat a metal one.